Recording now. We are recording, and where's this? Yeah. Okay. So welcome to. Yeah, it feels like eternity. Actually, it's been 2 weeks, but somehow continuation broke. Welcome to the next lecture of deep learning for NLP. So this is my last lecture today. Next week, I'm gonna hand over to Martin Tutek, who's going to take over the second part of the semester, and then the last lecture, one lecture maybe will be a guest talk on the topic of ethics in NLP by Thomas. So where were we last time, by the way? Okay, what was it? Word embeddings training, right? Anyone remembers what we did last time? Okay, word embeddings. So today we're going to be talking about recurrent neural networks, which is a super fancy name for things that are actually quite fancy. So the point is, so far we are talking about MLP, so multi-layer perceptron, and we squeeze some input in there. And for text with different lengths, we just said let's use continuous bag of words, right? Cram everything into one bag and just use everything, and don't care about the ordering, don't care about it. But actually, yeah, so this is what we did so far. And yeah, so we, as I said, we took as a concatenation of the vectors. So for example, previous 3 words when we were talking about language modeling. So predict the next word given the past 3 words. So we concatenated the word vectors. Okay, good. We then, what did we do? We also used the averaging, and we also used the Markov property, right? So we said, what is the Markov property again? Like previous 2-3 words maximum because of the explosion of the parameters or of the impracticability of learning the parameters. What we really want in natural language processing, what we really want is working with sequence of inputs, right? And we want to, for example, so give me a task where we have a variable length input and fixed size output. What could be, what could be the task? Like variable length input and fixed size output. Sentiment classification, for instance, right? Because we have these different movie reviews. If you remember lecture number 1, which was back in winter, feels like that. We had this very short movie reviews, like, oh, this is bad movie, and we have this super lengthy, 1,000 words reviews. And we want to somehow use all of them regardless of their length and predict maybe whether it's positive or negative. So this is one example. What we really care about in NLP, how we were dealing with that so far was just, kind of make a simplification and hope like it will work. It works to some extent, but there's better approaches, as we will talk today about. So this is a motivation for recurrent neural networks. And we start with a little bit of abstraction, what recurrent neural networks are actually could be, what's this like the interface of working with them, and then we talk about particle implementations of recurrent neural network. So let's have a sequence of input vectors. Okay, so what's coming in is not just words like or elements or items. We're putting in vectors, right? So what these vectors could be, well, they have same dimension. So the dimension of input, each of these vectors, and what these vectors could contain. So typically they would be a word embedding of the token, but it could be any arbitrary input like one-hot encoding and so on. So if we have a sentence, the cat said, and so on, what we are actually putting into our network is a sequence of vectors, and they have the same dimensionality dn. Right? So, and we have n of them, right? So this is times n, any arbitrary length. And we want our model to work for any n of what we choose. So nothing fixed, but some like depending on the input, okay? And what is in here, as I said, could be, typically we're using word embeddings, which are somehow pre-trained on as, what was that one? Word to vec, for instance, right? Okay. Any questions so far? Very straightforward. We're putting in vectors. What is the output of that? Is some vector as well, so of dimension d out. And well, we're now pretending we're plugging out, like we're kind of transforming the sequence of inputs into one output. As we will see later, it's much more powerful than that. And then basically our RNN, so recurrent neural network, is just a function from the input, a sequence of vectors, to one vector to the output. It's pretty, it can't be any simpler actually, right? So it's just sequence of embeddings or sequence of vectors in and vector out. Okay, any questions? So this is like the main interface to RNN is this. Okay, all good. So if you think about it, like what is the N, what does it mean? Well, actually these RNNs, this kind of simple interface is actually returning not only one output, but it's returning a sequence of outputs. Because for instance, if we have like N is equals to 3, so our input sequence is x1, x2, x3, so 3 vectors, right? And we're returning here, it's a typo, it should be y3, it's returning, you know, RNN of these 3 inputs. Okay, but actually the sequence also contains a subsequence x1, x2, right? So this is also, so this is 3 again, I'm sorry. So this RNN function, it takes a subsequence of x1 and x2 and also should return y2, okay? Because this is subsequence is part of this larger sequence. And if you take it to the extent, you know, to the extreme, then y1 would be RNN of x1. Yeah, because we're just, this is length 1, right? I mean, we're putting just one vector in and one vector out. So this is what we're getting for free, basically, by our definition. So this means that at each of the steps, 1, 2, or 3, the RNN is outputting a vector yi, right? Everybody's with me? Why is it so? Because we define it in a way, basically, and we said like, yeah, take everything in up until sequence of n, and then at the nth step, you know, spit something out. And obviously we have n sequence, you know, we have different subsequences, so basically at each step it's spitting something out, right? Any question? You might be asking why. Like it's kind of weird. Yeah, it's a way of defining things. So there might be advantages of this definition. So let's call the sequence outputting function RNN star, right? So we kind of we distinguish between a function which takes a sequence of vectors and spitting out a vector, and sequence of vectors in and sequence of vectors out, right? So the only thing which is important here is that it takes n vector in and spits out n vectors out. So the numbers, the n is the same. So we cannot, with this definition of RNN, we cannot do sequence of length n in and sequence of length m out. That's not what we're doing. Basically, we say for each input there could be one output. Gesundheit. Okay, so recap. Okay, so for a sequence of input vectors x1 to I, we have this output vector for the whole sequence, and we have this vector of sequence of vectors output for the same input. So without knowing what so the question is like, yeah, what is this function actually? Why, like, you know, what is in there? Well, before actually going deeper, what this RNN function should be implementing, what could be the advantage of such a function? So it takes 1 to n and outputs something. What is the advantage? And you know, is it any good? Like what could be in, for example, yes, yeah, okay. It does capture the context, exactly. But remember the language models we had before, like Ngram language model, it captures the context as well, right? So this is not the only advantage, but there's, sorry, I think you were first. It can remember something, yeah, Ngram language model remembers something as well. So, but you're right, you're on track, yes.
Can remember variable length context.
It remember variable length context because we're changing n, yes. If we change n in ngrams, it can also, but yeah, okay, I got you. Something substantial. Sorry. Yes.
It's 1 to I the same in every step, or does it change? Does the input sequence change?
So let's have document, let's have the cat said and bad movie. So these are two documents, right? So here we have n equals 3, and here we have n equals 2, and then basically if we can plug either of those things into this function RNN, and it will spit either one vector, or here 3 vectors, or here 2 vectors. Does it answer your question or not? Or is it something where I just made a typo here? Well, basically, yes, for each position it outputs one y, 1 epsilon.
Yeah, so at the end we have 3 y's, or is it like iterative?
Yeah, the last one, basically this one, the last one, this one is the last one of those sequence. I didn't want to draw any pictures here, but let me just try a picture. Maybe it will, I have much cool pictures later on. So x1, x2, x3, and we say, let's plug it into something here. I don't want to spoil here the something, so let's make it like something here, and it will spit y1, y2, and y3.
Yeah.
It's very abstract, right? Because this is going to be different and more complicated. Okay. Okay, so the advantages of the RNN. Yeah, so we are in context and we have different lengths. So this is good, but we have something maybe, if you compare it with Ngram language models. So Ngram language model we had sort of a simplification. It even had a name. The simplification in Ngram language models. We kind of got rid of it in word embeddings, but still we had some limits. So okay, maybe I'm asking wrong way. It takes the whole input. It takes it whole. We had the Markov property, so the name was Markov property because we are limiting to like k equals to 3, like k previous words or the window and so on. But now this thing takes the whole input sequence and produces whatever is coming out. So basically it's conditioning on the whole input. So we are actually overcoming the Markov property. We don't have to limit the context. Okay? Sounds great. So each output takes into account the entire history 1 to this position I without the Markov property. So the question is like, what are we going to do with this y? So there's a vector coming out of the sequence. So what can we do with that? And typically we use it for, as we were talking before, for some further predictions. So for example, we can plug it into softmax for a classification, multi-class classification. We could plug it into through some MLP, so multi-layer perceptron, maybe one extra layer, some projection into whatever two-dimensional vector, or 1 dimension, and put a sigmoid out of it if we do on top of it if we do binary predictions and stuff like that. Okay, so it's basically taking an input, making a transformation of arbitrary length input into either one vector or a sequence of vectors of the same length. Okay, so how does this work? Like, how can this actually work? Like, take any sequence of inputs and producing any sequence of outputs. So what could be in there? Like, there must be something happening, because how can you design such a function that no matter how long the input you pass in, it will kind of adapt to that. So there is one underlying mechanism here, and the backbone idea, and it's called states, because we need to pass the information between these like discrete states in time, as you wish. So from one time point to another time point and so on. So we're passing information from one position to the next. So from let's say we're at position Y, and the cat, and we're at position, so this is 1, this is 2. And here we have our tiny RNN thing. And here we have also RNN thing. And from coming to the next step, so here it's outputting Y1, here it's outputting Y2. And we're basically saving some sort of state, which we're passing to the next state here. So we're doing something in here, save it into some state, which we denote this as I, and we're passing it to the next state in time. So this is how we're keeping the information for arbitrary length input. So we're saying, well, something will be stored somewhere, and we just pass it by. What is in this state? It's an open question. Like this is part of these architectures, okay? But we are using a state vector to store something about the, the history, about the context from the very beginning, okay? Any question? So we can then recursively define these RNNs, which means that at each step y, what we have the current input vector. So this is maybe the word embedding coming in, and we have the vector of the previous state. So si minus 1. Now you might be asking if we're at the very beginning, so we have x1, maybe and it's going into our tiny little thing here. What is the previous, what is s0? What is the previous one, right? Because we always need a previous one. So this is the initial state vector, and typically, I mean, it's often omitted in the definitions, and typically it could be filled with zeros, maybe. There could be some special architectures where you need to initialize with maybe all ones or some random initialization, but typically it would be 0, okay? So at each step, we take the previous state and the current input and compute the current state as I. And how we're going to compute it, it's this beautiful function R as recurrent. And this is just basically an interface, right? So we're not saying what are we actually computing in there. We'll do something, and it really depends on the implementation, on the actual architecture of these RNNs. So we're specified at R later. But conceptually, we're just taking current word and the previous state and produce the next state and go on. Okay? Everybody's with me? Sounds great. Also, so we have the next state, but there's still something missing because we want to output something here, right? So this is the output at each step. So to compute the current output, again, we have what we have again at each step. We have the xi, so this is the input word. We have the previous state as I minus 1, so this is the same as in the previous slide. We already computed the next state. Oh, and now the output will be basically taking the next state and running some function out on top of that. So again, here we have, say, x1, it's this is the word. Oh, this is a bad example, I'm sorry. Let's make it generic. So we have xi, it's coming into our RNN thing here. We have the previous state si minus 1. And this is spitting out si. And what we're saying here, we're taking this this new hidden state and run it through the O function to compute the output. Okay. Some sort of transformation here. What exactly O could be, we'll define later as well as with the R function. So we have two functions. One is taking the previous state and input and computes the output, or the next state, and the second function is taking the current state and producing some output value. Okay, so two functions. Any questions? Good. So to sum up, at each step of the sequence of the inputs, we have the current input xi and the previous state, and we compute two things. So this is the current state using this R function, which takes into account the previous state and the input and the output. What is important here, that these functions, R and O, they can have different parameters as well. Obviously, they will be parameterized in a way. And these parameters and the functions will be the same for each of the positions. Because for each of the position, we'll have the same function R and same function O, taking our input and previous state and spitting out something. And if these things have parameters, the parameters will remain the same all over the whole sequence. So they will be like shared parameters. So here's a summary of that RNN thing. So yeah, it's basically repeating what's written here, but this is a simple kind of recurrent definition of RNN. I think it's time for some visualization of this abstract RNN, which is, yeah, you find in the literature, basically, most of the time. So again, this is the input we have at point Y. This is the previous, so this is a constant. We have the previous output, so this is some sort of vector, right? Because the state is a vector. And there are two functions, R and O, which are producing SI and YI, so the output and the SIs, right? And what is important here that if there's any parameters here, which we denote by this very fancy word theta, letter theta, the parameters will be shared for all steps. So at each step, the parameters will be the same. What is this thing? Why is there this an arrow? Yeah, because the recursion, exactly. Because the next step will be, I mean, this step will be previous step of the next one. Okay, yeah, that's not surprise. Yes.
But why do we need y, d, y, yi?
Because we want to predict something. We want to transform the state. So maybe the state could be the same as the output, right? Yeah, so right. This could be same as this, but maybe not. Maybe you want to keep some information, but output something else. We will see that later, because you maybe want to keep like a large memory, but just output like a vector for predictions, and they will be different. Sometimes they're the same. That's a great point. Any other question? Yeah, so this is like the, you know, there's this loop and it's kind of ugly. If you want to implement the thing, how do you implement this thing? Because we're talking about, so what is our backbone idea of doing NLP, doing deep learning and NLP? What is it? We have one core idea of doing deep neural networks where we compute all this bloody thing, gradients and stuff like that. What is that? What was that? One abstraction, like the most powerful abstraction we're actually working all the time with, underlying. Perceptron? The perceptron is an architecture, sort of. Yeah, I mean, it's a network, you have layers, but even like deeper, like the mathematical kind of concept there, or it's not even mathematical, it's computer science. Yes. You were first, I guess. I don't know. Yeah, and backpropagation running on something. So there is some underlying structure. That's the computational graph. The computational graph is where you run your forward propagation, backpropagation, and stuff like that. And everything should be computational graph. But here, like, I'm using the same colors all over and over. So these are trainable parameters or trainable weights, like the green lights, right? The green things are trainable. This is constant. And yeah, I'm using this as a sort of like intermediate gray things. Like this is a differential function. Yeah, right. So computational graph. There is computational graph under everything we're talking about. How do you compute this kind of loop in computational graph? Yes. Oh, okay. So you would say you wouldn't have a loop in your computational graph, so you wouldn't wire it as a loop, because how can you do backpropagation on a loop? Yeah, you can't, obviously. So you would say, let's have for each step one of those. Okay, yeah, that's a great idea. It's actually how we're doing that. Exactly. We're calling it unrolling. So we take this abstract thing, and then for each position 1, 2, 3, or 4, so here I have n equals to 4, I'm basically making sure that for each input there is this kind of the same thing and the same function R and O, R and O, R and O, R and O, right? So we're coming from this one with a loop and unrolling without a loop. This is a computational graph I could run backpropagation on, right? Because yeah, as usual, you go from, you know, the forward pass, and somewhere here you get back with the losses and gradients and all good. You can do that. Here's the interesting part. I mean, I really want to highlight that the parameters of these R and O function, if there's any, they are shared and are the same for all the positions. So this is important. We're sharing parameters, right? We're sharing parameters. So each of these units, or how you want to call it, like recursive kind of functions, are the same. If we train them, so if you can you train this with, you know, having theta applied to all these things? Can you train that? Could you train this network, or do you need some special hacks?
Yeah, I think we need some methods to combine the training directions that we take for all steps.
Okay, what could that be? I think there's even fancy name for that, and I think we had it before. I can even claim like we can do it right away with what we know. So this is going to be a multivariate chain rule, because you're going to sum up all the gradients here. And we had it already in you know, we had the share parameters in Word2Vec or in word embeddings, where you had just one A matrix, which was large, and kind of each of the embeddings was pointing there. We run it the same way. There's no difference, basically, right? Yeah, I mean, you were right. So we might need to tackle it differently, but we don't have to, because this is a graph we can work with. We can absolutely run stochastic gradient. We can absolutely run backpropagation on this graph, and it will work, because we have, you know, chain of rule chain for multivariables and plus and stuff like that from calculus. So this is easy to train. I mean, basically, once you, yeah, this is hard to work with, the recursion, but once you unroll it, you can just run your whatever backpropagation on that and train all the parameters you want to train, because there is nothing special about it.
So the input still doesn't have, for example, any role on Y1?
No. No.
But with text,
yeah, okay, that's a great point. So the question was that the X2 has no role in the Y1. So we're doing left to right. And maybe it's not a good thing, maybe it's a good thing. So what is the advantage of doing left to right processing in language? We read left to right, maybe we think left to right, time flies left to right. We're using the past for predicting the future, maybe. This is good. What is the disadvantage? You don't capture the whole context, because there could be interest. Because for this prediction, maybe if you're running, I don't know, thinking of a task like part of speech tag or entity recognition. Okay, maybe entity recognition. And here you still don't know all the information from the rest of the sentence, because there's some long range dependency. And maybe maybe the recognition is the best example, but maybe parsing. I mean, something very, you know, syntax, something very strange where you need a full sentence. So yeah, then you may think like, oh, maybe I can do something more fancier, and we'll do that. I'll come to that. This is the simplest left to right, but we might have something more complicated. Okay. Any other question? Okay, great. So this is our computational graph. We can run left to right kind of recurrent things, and we can train parameters. We still don't know what is in R and O. Yeah, so some fancy functions, maybe it will be simpler than that, but we'll come to it. So what can we actually do with such a network, right? So what could be the task? So we have conceptually two things we can do. And the first one is that we have this RNN as or acceptor on encoder. So basically, here we have our graph again, and we run all these inputs and you know, have this final output here. So at the last step, we have this output, which we plug into either softmax if this has number of classes, is y4, or the output vectors have number of classes. We might run softmax on top of that to get probability distribution, and then maybe predict a thing if this is multi-class classification, right? Or we can run it through much deeper, whatever we want, like plug it into maybe another network or some other parts, MLP, whatever. The point is that the loss for all these parameters, but basically the loss which gets backpropagated through all the gradients back to the beginning comes only from the last output here. So this is what matters. I mean, this kind of representation, what's coming out of here, takes the you know, has any value basically. And all these outputs are actually ignored here. We don't care what's coming out of here because we only care about, for example, here, encoding a sentence into a vector which carries the full sentiment of the sentence, which we can use for sentiment, basically binary prediction of sentiment, if this is binary thing, right? So we want to encode the whole sequence into one vector and then run something on the vector. It's not different from continuous back of words, but for that we kind of took each word's embeddings and made an average, and that was our representation. Here it can go much simpler because there's an ordering of these things, right? It matters which word comes first and which comes second, but the output will be the same. We have a vector representation of the whole input, and we can run it for some task, and then the loss the loss here will be propagated through the last point through the whole network. Okay, any question? Great. So this is one example. The other, we can run RNNs as a so-called transducer, which is super fancy for I don't know what's like, where it's coming from, like finite state machines, maybe finite state automata. I don't know. But anyway, the idea is very simple. So in the previous case, we had the full input going through the network, and we had the last output where we had a loss. But now we actually doing something called a sequence tagging, or this is a task. Typically, sequence tagging is done by this sort of architectures where we, at each of the positions, we're spreading out a vector, right? And then we have a supervised signal for each of these position vectors. So what could be a task that we can model with this architecture? What can you model with such an architecture where on each input position you have some output? What could such a task be? I think we had actually one in the very beginning in the first lecture, yes. It could be part of speech tagging, exactly, because then for each word here, like the cat, sat, on, and so on, we have the labels. So here it could be determiner, this could be noun, this could be verb, and this could be so on, right? So we would basically, for each word, we would split maybe one of the classes, right? Part of speech tagging, we didn't talk about part of speech tagging, to be honest, because it's just too low level. But we had something else where we had sequence tagging problem. What was that? Where you spit out one of several classes for each token. Anyone remembers that? It also had a fancy name. Exactly, name entity recognition. So for each word we would have, okay, so the cat said there's no entities, but maybe Jon Snow was killed. Was he killed? I don't know. That's a good question. Okay, something, right? And here the labels would be, sorry, the labels could be depending on your text set, how you define it, but I would say this is beginning of person, this is inside of person, and this is O, and this is maybe also O, right? So we're splitting a tag for each of the token sequences. And this is exactly what you're gonna model with recurrent neural networks, where you output as a transducer, where you output or you have a loss on each of that. So what is the loss here? Yes, I mean this is a one-hot encoding label, and this is a vector, and you have for example, okay, so what is a loss? Typical loss. I mean the only loss you should remember from deep learning for NLP. Cross entropy loss. Thank you. So he would run cross entropy loss. And the question is, okay, so if we don't have this sum above here, so we have a function computational graph with multiple outputs. Yeah, but we cannot run minimizing a function on multiple outputs, right? So we need to have one output only, which we want to minimize, the loss. There's only a single loss we want to minimize. So that's why we typically take all these local sort of losses and plug into a sum. So this is the final loss. So it's sum of these cross entropies for each of the position. Does it make any sense? Why are we doing this? Because we can only minimize function with one output, right? We have billions, gazillions dimensions in, but we only minimize one value. Because I know how to compare two values and say which one is smaller than the other. I can't do it with two values, right? So we just need one. Okay? Any question? Great. Okay, so we have this. So to recap, we have either taking last state and then running a classifier on top of that, or doing something very fancy, or taking each position and running something fancy on top of it and just summing up for the loss. We can train this as well. Yes, you have a question.
We then apply the same from the right to left, like in another case, or can we also start backpropagating on the middle?
So what do you think? I mean, how can you start backpropagating in the middle? So what do you need to compute for the backpropagation? What you're interested in backpropagation?
The end sum of all the loss.
Right. So this would be your, let's call it E as an error. And what you're interested in is a partial derivative of your error, of your loss, with respect to all these parameters. And so on, right? This is what you want. You're updating the parameters here, and this is your final value. This is like your output of the loss, and you want to minimize this function. So you have to start from here. But I mean, well, you're starting like the forward pass, you're starting from the input values. You kind of compute all these intermediate values, and then you say, okay, this is my output, and I'm starting with this part, partial derivative of E to E equals to 1. And then I'm going to the children of this node and doing this local derivatives and so on. I mean, basically the very same stuff we did in the second lecture, but you start from this single loss, like this error or loss, or how you call that. So you go from the beginning to the top, and then here you're backpropagating. Of course, I mean, the topology here of this network is kind of complicated because, well, it's not. It's only deep. Basically, it's a deep network, but you can't do any wrong. I mean, if you apply the rules of computing from the last node to the children, and then back to the children, and to the children, and to the children, you will finish with the full gradient. Does it make sense?
Yeah.
Okay, cool. Any other question? So I'm coming back to your question actually here. How to make it, can we look into the future and use the future for some current predictions, right? So how would you, for example, what would be like so now you know this recurrent networks, what would be like the most simple solution for this problem, where you say, yeah, for representing the sentence, I want to take like left to right and right to left. What could be like this most simple solution you could use? You want to have a vector representing the whole sentence, and this vector should have the representation which is learned left to right and right to left. How could you solve that? Running twice. And then add them up. Okay. So you would like sum them up or something else? Say again, maybe the average. Okay, yeah, that's not really far away from what we would do. So we say run one RNN from left to right. We call this a forward, and another RNN from right to left. We call it backward. So this doesn't have to do anything with forward propagation and backward propagation. Nothing at all. It's just left to right and right to left, right? So these are false friends. And then typically we concatenate them, right? We take one vector from one direction and then concatenate the vector from the other direction, right? So what does it mean? If I have the cat set, I'm running one RNN like that. And here comes one vector. And then I'm running, let's say, one RNN from the right-hand side. It's really hard to draw from the right-hand side. and I'm getting another vector. So let's call it YF like forward and YB as backward. Then I'm gonna take these two vectors and just concatenate. That's it. Right? How can I create a loss? Yeah, and the loss will be the same. Basically, I would sum up the losses from one side and the other. Basically, no, well, I don't have to sum up the losses because then I will run my maybe classification on this node, and everything will work out because it's just a computational graph. Okay, so there will be nothing very special about this case. That makes sense? Okay, so basically we're saying we can look into the future for predicting the present. Yeah, fair enough. We can do that. We did it already with word2vec. Okay, so the big question now remains, what is happening inside this RNO, right? So what are these functions actually doing that it works like? I mean, it could work like that. Theoretically, we talk about the interface. At each point, input in, previous state, and some output, and something very fancy, and next state. Okay, what is in there? So, what could be the simplest recurrent neural network architecture? We call it simple RNN. I think it comes from the 1990s. Is that here, excuse me, we have a so for computing the next state Si from the previous state Si minus 1 and the current input, we just say, okay, let's take the previous state and multiply by some weights, some linear projection, take the input, also do some linear projection, add some, what is this? Bias. We add some bias. So this is just linear mapping from the previous state and the current state. And this is some nonlinear function. Nothing more. So just basically linear transformation and some nonlinear transformation on top of that. Okay. Any question? So yeah. So we're saying take the previous state, apply some linear projection, take the current state, apply some linear projection, and sum them up, and run it through some nonlinearity, because it's better to have nonlinearities, because if everything is linear, the rest is linear. So the whole thing is linear. So there is some typical nonlinearities like ReLU or TAN H. Then for the output, we're just basically saying, well, this is the state, right? So there's no fancy function. We just say this is Si. You were asking before why we need this. Yeah. So in the simplest case, we're just spitting out the state, and it's fine. It's fine enough. Okay. So this is very simple. What are the the devil is in the details. So these three matrices, I mean, two matrices and the bias are obviously learnable. So this is what you learn during backpropagation. But given this is like a computational graph, you can learn it basically by backpropagation in a very nice way. So here are some dimensions. I'm not going to go through the details right now, but everything has to kind of work out in terms of multiplying vector and matrix. This is still the same. So you have to pay attention to the dimensions of those things. And the nonlinear function, as I said, it's 10H or ReLU. Great. The problem here with this kind of approach, the simple recurrent neural networks, is so-called vanishing gradient, because this is in fact like a very deep network, and you're multiplying with the matrix W over and over. So if you're running from here, and the network is really deep, so here you're multiplying lots of gradients, and they become extremely close to zero. So it's called vanishing. So they vanish, they kind of come to the zero. And the point is, if you have zero gradient, what happens? You don't update anything. So updating information like from the beginning of the network gets harder, because the signal is just far away. So the signal is at the end of the network. You have like lots of some meaningful gradient, but when you're multiplying over and over, small numbers, small numbers, and then you end up with zero. And that makes it hard for RNNs to train, basically, and to capture like long-range dependencies. So this is nice and simple, but a vanishing gradient is an issue, right? Because you want to keep information from the very beginning for the whole sequence. If you have the problem is, like, if you have long-range dependencies problems, you have to have solution which kind of pays attention to which can solve long-range dependencies. And the simple RNNs, they can't do that. So you need something much better. Okay. So vanishing gradient in this, we call this sort of like vanilla RNN as well. vanilla RNN. So simple RNN, vanilla RNN, just nothing fancy. Just these two functions, basically. Linear projection and nonlinearity. So we need to do something better. And now we come to this so-called gated arc. Any question to that? Vanishing gradient. Yes. Why the gradient vanishes? Because the network is well, because of the depth of the network. Like in the deep networks, you have the issue of propagating the gradients from the, so the signal comes from your output node. And then you're multiplying by these local derivatives and so on. And the more multiplications you have, the closer in some cases to zero it can go. And then you have basically very, very few updates in there. So what you would typically do is maybe training. So it was like back in the days of early training of RNNs, of deep nets, was freezing layers and training like half of the network, and then training second half of the network and so on to overcome this. And in RNN is an example of this, deep network. So this is an issue. Yes.
Does this assume that we condition the data, the input data, or because like when it's not all the probability distributions of between 0 and 1, could it be also bigger than 1 and just having exploding gradients?
The point is, yeah, you can have both. I mean, this is the thing. You have 10H, right? So in 10H, your gradient goes to 0 on both parts. That's the right. I mean, you have something in the middle. There is a nice signal you're having in 10H. So let me just draw 10H. So roughly. So 10H is nonlinear function we're using, which is great. So between minus 1 and 1. But here, roughly, and from here, the gradient of the 10H is coming to 0. And then you have this issue of multiplying by something very small. If you have ReLU, yeah, this is great. In ReLU, you can have exploding gradients. Yeah, I mean, exploding gradients are easy to handle because you can just clip the norm maybe or something like that. But vanishing gradient is an issue here. And ReLU actually wasn't invented before. I guess ReLU is kind of new conceptually. So previously, deep networks were sigmoids or 10H, and then you get this issue of vanishing gradient because the gradient is small, in these nonlinearities. So does it clarify that enough? Good. So we can use the gated architecture, and what does it mean? So if you look at RNN, it's just as a general purpose computing device. Yeah, it's a very brave statement, but anyway. So the state Si, which is the vector, it's basically memory because you're passing this state from one step to another. So it's sort of a memory of the previous states. And here's just for recall, we give the function for the simple RNN where you have the state multiplied by some weights, and you have the input multiplied by some weights and adding some bias and running through some nonlinearity. But this is important part because each application of this function R, basically it reads the current memory Si minus 1. It reads sort of the inputs XY, operates on them in some way, basically this addition and multiplication, and it writes the result to the new state Si. So we're reading the previous state, we're reading the input and writing to Si, right? Like in a very abstract way. We take the memory, we take the input, do some operation, and write again to the memory. Everybody's with me on that? Yes. Okay. So we're accessing the memory, and the access is not controlled because at each step, the entire memory state is read and entire memory state is written. So we're taking previous state, the memory, we take the input, do something very fancy, and save the whole memory again. Like we're overwriting the whole memory with the result of the computation of the previous memory and the current memory. So we're rewriting the whole memory. It might be a good thing, might be a bad thing, but it turns out it's not that, that's not what we want. We want maybe something where we can control the access to the memory. So how can we provide control memory access? let's have the memory, so we call it now S, just memory vector S in some dimensions and the input vector X in some dimensions, right? Just now just abstraction. So we have two vectors, this is the memory and this is the input. And let's have a binary vector, which we call the gate, which is just the zeros and ones of the same dimension. Okay, so we have now three vectors. Memory, the current input, and we have something which is called a gate. And this is just zeros and ones. So here's a very fancy thing, which is the element-wise multiplication called Hadamard product. I don't think you have to remember, but maybe you can remember this. But it's just basically very fancy name for element-wise multiplication of two vectors. So you take each vector, each position at one vector, multiply each position in the other vector, and this is the result. And I'm using this kind of circle and dot for that. Okay, so Hadamard product basically element-wise multiplication of two vectors. Now, anyway, if I have this this memory vector and the input, and we have a gate which is just zeros and ones, then I'm gonna use this sort of operation to control the access to the memory. So what does it mean? So I'm gonna take the entries in X corresponding to ones in G, right? Because if I multiply something with, so the G is 0 and 1s, and X is just real numbers. So what I'm end up here is just taking the values in X for which the G is set to 1, right? It's basically like masking. So if G is zeros, this output will be 0 for this particular choice. So I'm reading the entries of X corresponding to 1s in the gate, and I'm gonna write them to the memory. And in the next part, so this will be so 1 plus G in binary means I'm flipping the bits in the gate. So now I'm taking the rest, the remaining parts of the gate and reading from the previous state and saving to the memory. So if it looks very weird, let's work on an example here. So I have an example on the next slide. It will be much clearer. Okay, so here's our formula again. And I have, so this is, okay, what we have here. So this is vector X, and this is the state, so the previous state, and this is our gate. So the gate is given, I just made it up here. So our gate is 0, 1, and 0. So this is our gate, G. And this is the input, and this is from the previous state, so the memory. So what I'm doing here first is I'm just multiplying this element-wise. So basically saying this will be what? 0, because 0 times 10 is 0, 1 times 11. I'm basically masking the second vector with the gate. Right? Everybody's with me on this operation? So I'm multiplying these vector element-wise, but basically it's masking by this mask. Okay? Good. So here, 1 plus G, it's gonna, this is the flip of this, right? Because in binary, I'm just making from zeros ones and from ones zeros. And here, oops, excuse me. And here again, I'm just masking the memory vector. So what's coming out of here is 8. Here it's coming 0 because it's 0 in the mask, and here it's coming 3. Okay. So here I basically masked the input, and here I negated the gate and masked the memory. And because they are, different in different positions zeros, adding them together will keep me the new input from the current state, and from the rest will be kind of stored from the previous memory. Okay, does it make sense? Why this masking works like control access to the memory? Basically masking one vector and using the negation of the mask to mask another vector, and just sum them together to get kind of this gate controls what gets new basically to the memory. Okay, any questions? Yes. we are not at all in matrices, or sorry, in embedding the weight matrices, nothing. I mean, we are just, this is just completely out now of the of deep learning or whatever. This is just how you have, if you have a vector of memory, if you have a vector of inputs and you have a gate, how you can combine them together to save something from the input and keep the rest of the memory. This is like a side step, okay? But you might be asking, why the heck are we needing this, right? Why is it important for deep learning now, right? So we can use these gates for RNN because we want to, control access to our state over time. But here the gates are, the gates here are not learnable. I mean, we're kind of given this or made up. And these gates are not really differentiable. Hard gates, like zeros and ones. Yeah, this is, zeros and ones are bad for, for differentiation. So this is not good. So we're going to replace them with so-called soft gates. So how can you, okay, one idea, brainstorming. So can you replace this with something which will give you something differentiable and close to 0 and 1s? We have a function which gives you something almost 0 or 1 and is differentiable. We have a function which, whatever it comes in, gives you either 0 or 1 almost. Sigmoid. Sigmoid is differentiable? Yes. So maybe we'll use somewhere in sigmoid to get something which is almost 0 and 1, and it will be used for gates, maybe. Okay, yes. So we're coming to one very famous and very interesting architecture of RNNs. It's called the long short-term memory, LSTM. So it fixes two things at once. I mean, not fixes two things at once. It fixes the vanishing gradient problem. And it's also the first one which introduced this gating mechanism into RNNs. Okay, so now LSTM splits the state vector exactly in two halves, right? So we take one half of this state vector as a memory cells, and the second will be something like called working memory or something like that. And this is also the answer to you, like, well, we can spit out the state as output. But here the state will be more complicated. We have two vectors in the state and they have special meaning and special role and they don't interact that much, okay? So the memory cells are, they are designed to preserve the memory and the error of the gradients over time. And we have this differential gating component. So we will have some gates and which works as almost as we had with these binary gates, but there will be completely differentiable, which makes them learnable in a way. So they will simulate the logical gates, right? So that's why I think it's important to understand how these gates kind of work before you see the Hadamard product in LSTM and just like, why? What is this? Maybe it's like, why? What is this? It's complicated, but anyway, I hope we'll get through that. Okay, so LSTM. So as I said, like the state so I'm switching now indices from I to J. Okay, so it might be confusing, but there will be something with an index I which will have a different meaning. So now we have our input is 1, 2, and J, 1, 2, and J. Okay, so this is the position in the input. It's not I anymore. So the state is now two parts. So the memory component, which is a vector, and the hidden state, so-called component at position J, it's also a vector, and they have the same size, these two things. Okay, so this is just, we're setting up the scene now. And at each input state J, the gate or a gate decides how much of the new information should be written to the memory and how much of the current content of the memory should be forgotten. Yeah, this is similar to what we had before. We said like, use the gate for keeping some information from the memory and use a gate for adding new inputs to the memory. So here it will be more complicated. We will have multiple gates, but their function is the same, basically selecting like 0 and 1s almost, zeroing out information which should be ignored in this step and keeping 1s for the information that should be kind of important in this step. So there are three gates in LSTM: the input gate, the forget gate, and the output gate. We'll come to that exactly right now. So let's work out through the LSTM architecture. So what we have here again, we have this this memory cell from the state before, and we have this working memory state from before. Okay, so this is these two things together is the Sj minus 1. So this is the state. Okay, and here we have the input. Any questions? Good. This is great. I mean, we have, there's no surprise here, just to understand we're on the same page, because it might get complicated a little bit, but we have to go like, step by step. All right. So we're gonna do one thing. We're gonna take the previous hidden state, and we're gonna take the input and create something which we call the update candidate. So we're gonna take these two parts. And again, we're multiplying the input by some matrix. So this is some linear projection. We're multiplying the previous hidden state by another matrix and going through some nonlinear function, which is 10H here. Okay? Why are we doing this? I mean, this is basically the same as a simple RNN. We take the input, projection, previous state projection, and adding them up and using some nonlinearity function in there. Okay, everybody's with me? There is nothing substantial new, as opposed to these simple RNNs. Okay, good. So this is our update candidate. Great. We're gonna do one more thing, which will be almost the same as this one. So we're gonna take again the previous hidden state and the input as well. Again, we're gonna compute, multiply by some weight matrix, and add the previous, also multiplied by some weight matrix. So what's the substantial difference here? What is the substantial? Can you spot the substantial difference here? There's two differences. Okay, here we use sigmoid and we use 10 here. Okay, another difference. We have different parameters, exactly. So we have these. This one is indexed by HF and XF. So basically it means like I'm multiplying X by the matrix for X, and the F means this will be the forget gate. Okay, this is it. Forget gate. Nice. So these are different matrices than these, right? They will be different. They will learn something else. And why is it the gate now? Because we saw before the ones and zeros, and we know what sigmoid is doing. We know what's coming out of here, right? From this thing, it's coming some sort of something between 0 and 1, and mostly will be 0. We want it to have almost 0 or almost 1 for things that should be forgotten and for things that should be not forgotten. This is why it's called forget gate. And this is why it goes through the sigmoid. Okay? Everybody's with me still? Good. Now we're gonna do something else and the same. We take the previous hidden state, we take the input, and again multiply by some weight matrix. This weight matrix is different from this and different from this because it's called xi. This will be the input gate. And we're running this again through sigmoid, so it will be again mostly zeros and ones, but it's differentiable, so it's like kind of hard binarization. Okay, and we're running that. So there's input gate. Okay, so we have this update candidate. Yeah, why is here 10H? I don't know, maybe like popular choice. Could be, I think it could be ReLU in theory, but in LSTM it's 10H. But here the sigmoid is important because the sigmoid is saying, well, it's a gate. It should be either 0 or 1 mostly, but we cannot do it hard, so we have a differential diversion. So we use this kind of binarization through sigmoid. So we have two gates, forget gate and input gate. What the heck are they doing? Well, we don't know yet. We're not there yet, but we have something with different parameters. So they will learn something different. They should learn something different. Everybody's with me? Any questions? Good. Now, if you recall from the previous slide, let me just come back a little bit. If you recall this thing, like this formula, roughly, where you take a gate and multiply by input, and take another gate, sort of, and multiply by the memory, right? So this is what we did here to update the memory. We're not gonna do something much different from that now. Okay, where are we? Okay, input gate. So we're gonna take the previous memory cell and multiply by the forgot gate, right? So we're gonna kind of forget something from the previous memory, and we take the input gate, and here this is our input candidate or update candidate, and we're gonna again multiply it by the gate and sum together and save it to the next memory. Okay, so it's basically very similar to what we did before, but here we kind of learn these gates. So we learn this. This is coming from these, oops, sorry. This is coming from these previous kind of transformations. And this is the previous step. And this is our input, but the input was transformed through some transformation, some projection. Yes.
I'm just going to make the product of I and T, but they both come from XJ. Why do I first do separate I and T and then put them together?
Why you go from X to Z?
Yeah.
And why you go from X to Y? I mean, X to I is clear because you need to make it a gate. Why you go from XJ and not like that? Yeah. Because maybe your representation of your input should also take into account the working memory from the previous state. Yeah, because you want to learn something from the past to represent the input. I mean, it's implicitly here as well, right? So you could theoretically do that, but also I think you can learn some interesting mapping here. That, I mean, I don't have an answer like why is it so, and would it work with like plugging directly the input? Maybe it will work. If you pay attention, I mean, the XJ has to be the same dimensions as the I's, obviously. But theoretically it could work, yes. But here, like just an extra bunch of parameters to learn this thing and projecting and taking into account here for this kind of learning, also the previous one. That's how they designed the LSTM. I think I'm not sure, I have to check. I mean, there's this gated recurrent unit, GRU, which is simpler than LSTM, and there's some simplifications with the gates, so there's not so many gates and so on. Maybe they're doing something like that, but I don't know by heart. Yeah, fair point. Any other question? Okay, good. So what we did so far, we have a input, previous memory, and we create a current memory. This is great. Yeah. So what is missing still there? We need still, what do we need to do? We need to calculate HJ, and we need to calculate and the output, Y, exactly. So two things. Let's start with the output. So we're going to introduce another gate, which is called the output gate. And here we're doing again the same thing over and over. So we are multiplying by the input by the weight matrix, multiply the previous hidden state by the weight matrix, and squishing through the sigmoid. Okay. So this is again another gate, and there's different bunch of parameters, but conceptually it's another gate. So we have three gates: forget gate, input gate, and output gate. And the output gate is going to control what? It's going to control what we are going to output to the next hidden state. So now we're taking this gate, we're taking the current memory, which we run through 10H. Don't ask me why, I don't really know. But basically we're running through 10H and multiply by this output gate, this Hadamard product, and this will be our next hidden state. Right? So basically there will be this sort of recurrence from these two states and these two cells like the vectors. Okay. And the last part, what is missing is to compute the output, and the output is very simple. It's just the hidden vector. So this is what we are outputting here. We're not outputting the full state. We're not outputting we're not outputting the full kind of memory and the hidden state. We're just outputting the hidden state. Okay. So this is the full LSTM, which looks kind of complicated, but there's 3 gates, and the gates have a meaning. So what they're doing, they're learning something about how much to forget, I mean, what to forget and what not. And there's a couple of weird choices. To be honest, I have to check why there's 10H, I don't know. And everything is differentiable, and everything kind of you can train in computational graph. But it looks complicated. So that's why there's newer versions of GRUs. Yes.
How's the state vector split?
The state vector is a half and half. Well, you would treat it as 2 vectors basically. You would treat this as, let me see. I'm coming to that in the next slide. Okay. So you would have CJ and HJ have the same like hidden dimension. So this DH is dimensionality of the LSTM, like the hidden layer size, and all of these. So this vector and this vector have the same size, which means the output vector has the same size, and all the gates have the same size, obviously, and the candidate vector also has the same size, which is the size of the like hidden layer, like a parameter of the LSTM. And why there is this transformation also means that the dimensionality of the input could be something else than the internal workings of the LSTM. Yes, you have a question. Because you're keeping here you're keeping things here in the cell memory, and it basically it's they call it like memory highway. Basically, it keeps the information stored over over longer kind of input. How exactly to work? I mean, I can't do the math right now. I don't know, but it's there are definitely proofs saying, yeah, if you have this memory which is kept and updated, just because you update only the information you need at a point and not overwriting the full memory. So maybe that's why. But to be honest, I don't really know how exactly, why exactly that works as it is. Yes, you have a question.
If you use the same parameters for every part, wouldn't you just never update the memory? Like it's set once at the beginning and then it's never overwritten because the gate never allows it to be overwritten at any later point.
Can you? I don't understand.
Like if you, for example, if you have like a gate for a vector that's like 0, 0, 1, and the first 2 are like the memory that gets overwritten by the working memory by the next state, then whatever you set at the beginning of the memory will just never get overwritten, because every time it gets to that, it's like, yes, we get to the next vector 0, 0, so we don't write anything to memory, we just write our last part to working memory, and then we get to the next part, and then that happens again, so the memory is just never changed at all.
Sure, but in general, it should be learnable through. I mean, you're penalized that. I mean, if it doesn't learn anything, you penalize it by a huge loss. So
I feel like that's inherent to the gate mechanisms. If you have a memory, that's like if you have a memory gate, that's the same for every single.
Yeah, but it's parameterized by the. So look at this. I mean, the memory gate is parameterized by the current input. It's the point. So whatever comes in, it will change the gate. So if you have different, I mean, and you have different words, like different inputs at each position, so the gate will be different based on the word coming in. So it won't be the same. I mean, you don't have a static gate, you have a learnable gate. And the learnable is conditioned on the input and the previous hidden state. That's the trick. Like you're taking the full context. So here you have the full context of the previous things, because it gets it gets to here. So this is the recurrent part. You're running this over and over. You keep something in the working memory. You keep something here as well. But okay, for the gates, you're taking all the information from previous steps, which by the way depends also recursively on everything, right? Because the HJ takes the whole thing here, like the long-term memory and the working memory. So you're conditioned on that and conditioned on the input. So you will output a different gate for that. Yeah. Okay. Sorry, where are we? Yes.
One more question. Do we have a round color gate with 0 and 1?
No. It's you don't. I mean, you want them to learn that they are either very close to 0 or very close to 1. Yeah. And if you think about the sigmoid, you will end up there. So it will be like very soft, but mostly 0, mostly 1s.
So we just accept that our save operation takes away a bit of the...
Exactly. Yes. Yes. Exactly. It's soft. So you have something. You have very little addition from everything, but you prefer those which are kind of very close to 1. I mean, they're got yeah, they're weighted by basically by these 0s and 1s. Yeah. Okay. Any other question? So okay. Here, basically, as a layer, so this is again the abstraction we had before, so the recurrent abstraction. So we split the state vector into 2 parts, which could be concatenated here. But there are two different vectors basically running through the state, through the LSTM layer, and we have the input, and basically all the parameterization are all these different matrices. So for each of the each of the gates, for output gate, input gate, forget gate, and this is the update candidate. We also didn't add the bias term, but you can have, theoretically, you can have in all of those, you can have a bias term here, plus bias term, plus bias term, plus bias term. So you have, more parameters if you really want. I didn't put them there, but they're, you just ignore them for clarity. And this is it. Basically, you have these were our RNN functions, but in a very fancy way. So we have gates and we have all these products and stuff like that. Very many parameters, but they're there. Okay. Yes.
So you're basically learning gates.
Yes.
As you go.
Yes. You learn the gates as you go, because the gates are just the gates are vectors. So you learn the projections based on your input and previous state. You're learning gates. You learn what to remember and learn what to forget. This is the power of these LSTMs. Okay. Any other question? Good. So that was fast. I think I had some questions for you, but I forgot all of them because of this. I mean, it's complicated. So the question is like, should I remember all of these? I don't know. You should. I don't remember it either by heart, like all these tiny details. But you should remember there are these gates and what they're doing, why are there, and conceptually how that works. The point is, so recap. We have RNNs for arbitrarily long input. So this is the big advantage of them. And they can encode the entire sequence and basically each step of that, as we saw before. We have the bidirectional RNNs, so we can model from left to right, right to left, and combine together, which is great. And we have the gating mechanism to effectively work with the memory cells. And LSTM is a particularly powerful RNN. You might want to look up GRUs. So this is from, I guess, 2012, 2013 maybe, and it's quite simpler than LSTM, but LSTM is nice because it shows the gating mechanism, in its full power. Why is it important? And we're really fast today, so I don't know. Anyway, so thanks a lot, and next week, actually, I'll be here as well with Martin, but Martin will take over, and we'll be talking about generation with RNNs. So thanks a lot.